All right, welcome. We're still in the realm of transforming one form of a quadratic equation into another. And this is one where we're going to take, starting from vertex form, which looks like these. This is the one that has the parenthesis grouping, the second power, and add or subtract a constant. And we're going to transform that into standard form. And standard form where it's just an x squared plus or minus an x plus or minus a number. Okay, so this one, again, vertex to standard. So here is our problem that we're going to work with, and I should put, just to keep in the realm that we're talking about functions, here's this f of x notation. That gets suspended as we work, so we can just repopulate it into our answer when we are done, but we don't have to necessarily keep that as we do our work in this problem. So when we're doing this, we're going to expand out into standard form. So our final answer might have up to 3 terms. And so we have to decipher the notation hiding in here. So remember, mathematicians are super efficient. And so this is a code. This is not x squared minus 9. That's not equivalent to that. There's actually a middle term hiding in there. And that's something we need to always remember, that x subtract 3 all squared means it's x minus 3 times x minus 3, right? We know what squaring means. If it's 4 squared, it's 4 times 4. So this means it's this quantity times itself. Without this step, you'll miss a term. You'll miss the middle term. So it's really important to remember how to expand a quantity squared. And that's true for a quantity tripled, quadrupled, and so on. So now we're doing distribution. We're going to do x times x is x squared, negative 3 times x is negative 3x, and should have done for this arc visually, negative 3 times x is negative 3x, and negative 3 times negative 3 is a positive 9, and I bring down the negative 1 that was hiding in here, okay? So now I just scan through and combine like terms. So those are like terms and these are like terms. So I'm left with x squared minus 6x plus 8. And that right there is standard form. So we went from vertex to standard simply by expanding the notation of a quantity squared to its proper format, applying distribution, and then combining like terms. And don't forget to always include this value at the end, right? This portion of the vertex in our formula into the constant that you create from your distribution process. All right, so there'll be a second part. I'm going to link on to the same video to go in the opposite direction. I'm going to forewarn you to go from standard form to vertex form. Takes a whole different process. It's going to feel a little brand new, but it's based on all the skills you've been learning. So I think we're going to be okay. Just follow along, pause the video, and we'll get at it together. See you in a minute. All right, so here is the second part. We just in the prior segment of the video transformed from vertex into standard form. And now we're going to talk about how do you go from standard form, which is an example here, into vertex form, where you have a quantity squared plus or minus a number. Now, this process is called completing the square. So the idea is we've seen what happens when we have a perfect square trinomial or a trinomial square. It's where the two quantities are identical. So think back to the prior segment. We had x subtract 3 and x subtract 3 as the repeated quantity. That's what we're trying to create because that was from a perfect square trinomial. So the way I outline this process, and I think I'm going to write it just so it's less toggling with the keys. So we have the general format is to take the first 2 terms, keep them on the left, prepare a space. We're always going to add something, but we don't know what yet because we're actually trying to complete this as a trinomial square. And we're actually going to have moved this constant 8 because it's positive, and we're going to locate it to the other side of the equal sign. We're subtracting it to the other side because notice I didn't write the 8 anymore. I subtracted, so I could show it this way. I subtracted 8 from both sides, okay? And then because the rules of algebra say whatever you do to one side, you must do to the other, and really we can willy-nilly and add, subtract, multiply, and divide anything we want to an equation, even if it doesn't help us solve for the variable, as long as we do it to both sides. So that's kind of what we're doing here. We're going to add something to the left, but we have to add that exact same thing to the right. And so I'm just preparing visual spaces so we know that we're going to have numbers that occupy here in a moment. So the process is we have to figure out what number goes here so that when this gets factored, I create two identical quantities. And so there's a little pattern trick here, and this is a little side note I'll put over here, is you take the b term and you divide it by 2, take half of that, and you square it. And this gets you the mystery number that you're going to put right in here and in here. Okay, so what is the b? Well, that's because in our generic equation of a polynomial, or sorry, of a quadratic, it's ax squared plus bx plus c. So these a, b's, and c's, which you've seen with quadratic formula in your prior math learning, they're your coefficients from your second degree polynomial. And so when we look at the b position, it's with the linear term. So we go to the linear term here, and we see that b is -6. We have to we can consider the sign here. This is one where you could be a little flexible and ignore the sign or not, because no matter what, if this becomes a positive number and we square it, well, then the outcome's positive. If this outcome is negative and we square it, the outcome's positive anyway. So this is like a foolproof system, not only of finding the square, but of making sure we have a positive outcome also. So if this is a -6, I'm just going to plug it in, -6 divided by 2, we're going to square it. Remember, your order of operations, do inside the parentheses first. -6 divided by 2 should get us a -3. -3 squared gets us a +9. And it's the 9 that's the mystery number we were trying to uncover, okay? I'm just going to delete these arrows so they're out of the workspace. All right. So the reason we did this was so that we could complete the square. So watch what happens when I factor this. So I'm going to do our typical standard to factored procedure, see how that process is tucked into this one. And so when we factor, we're going to have x and x. We look at the last terms. We need two numbers that multiply to 9 and add to 6. So 3s are the way to go, but we have to look at our signs. So we can only add to a -6 if both are negative. And since negative times negative is positive, we regain that 9. And over here, we are left with -8 plus 9, which should get us a +1. So this is, if you don't get identical quantities at this step, that's your clue that something went awry and we need to start again in a different pathway. So we want these two quantities to be exactly the same in element content and sign. And that's because we can consolidate this, right? Because anything times itself is that value squared. So that's why we can rewrite this now as x minus 3 as a quantity squared, right? And now we're going to, actually, I'll just write it like this so we can see it. And now, though, we're going to subtract the 1 and bring it back. We only move the constant, so it's just out of the way. And so we know what happens when we combine the mystery number with that constant, that our additions and subtractions are properly done. And so what we have here now is x minus 3 quantity squared, subtract 1. And it does equal 0 here, but let's just put it back into our function format, our f of x notation. And so now we moved from standard form to vertex form with a process called completing the square. So this is what I mean by there's some different thinking going on, right? There's a little bit of a parlor trick happening to find the mystery number, but you can realize why this works if you really look closely back at your distribution and factoring, moving back and forth. You'll see this pattern is there for our perfect squared trinomials. So if it was x plus 4 times x plus 4, you'll see that the relationship between the b term and the c term in that original trinomial in standard form is the same relationship that this is illustrating for us here. So it's not really mystery science. It kind of looks that way, but it's founded in a pattern in the math. Okay, so this is a tricky new concept, but it's very doable. So feel free to back up the video and watch it again and listen carefully to the thinking I'm trying to outline here of identifying our mystery numbers so we can complete the square, so we can have the quantity repeat itself, so we can square it, have it in a squared shorthand notation, and thus we can build our vertex form. Notice this form told us the y-intercept was at 8. This, that standard form told us the y-intercept is at 8, and then this form of the quadratic tells us the vertex will be at +3 and -1.